Hello, everyone. Welcome to the Pulsar Summit 2021. In this section, we will go through a Pulsar use case in the Federated Learning area. I am Jiahao Chen. I'm engineer at VMware. My department is OCTO, OCTO, the Office of CTO, and I am focusing on cutting-edge technology like Federated Learning, MPC, and Cloud Native. Here's the agenda of this section. Firstly, we will go through the background of Federated Learning, including the definition of Federated Learning and its implementation, the FATE project. Secondly, we will talk about why Pulsar is needed and the overall architecture of the FATE on Pulsar. And then we will have a summary. So what is the Federated Learning? As we all know, the success of artificial intelligence relies heavily on the quantity and the quality of the data to train models. However, due to the privacy protecting laws like GDPR, the organizations cannot share its data with others, which brings some challenges to the AI industry. The Federated Learning is aiming to address this kind of challenges. So on the right-hand side is the basic concept of the Federated Learning. So the raw data of all parties is stored locally, ensuring that the data is protected. Instead, some encrypted data during the training, like the logs and the gradient, will be transferred. The modeling performance of the Federated Learning is same as the modeling result achieved through the aggregation of all datasets into a single party or to a center server. So I would like to emphasize the cryptography in the Federated Learning. The first one is the homomorphic equation. I will give some introductions in case someone is not familiar with them. Homomorphic equation allows operations on encrypted data, which has the same result on the plain text data. And it's a natural primitive to implement outsourced computation. With partially homomorphic equation schemas, only certain operations can be performed. Several efficient partially homomorphic equation schemas are known, like the Pulsar. So in the FATE project, which we will talk about later, has implemented the Pulsar by Excel. So the system built on the partially homomorphic equation are limited to specialized problems that can be funded in terms of the supported operations. To provide fully homomorphic equation, it is necessary to support a universal set of operations, so that any infinity functions can be computed. Although the FHE fully homomorphic equation is fancy technology, its cost is huge, which makes it not practical. So the goal of the secure multi-party computing is to enable a group of independent data owners who do not trust each other or any common third party to jointly compute a function that depends on all of their private inputs. MPC differs from the outsourced computation in that all of the protocol participants are data owners who participate in executing a protocol. So as for federated learning, let's take a look at this and the logic. We take the sheep as the machine learning model, and the grass is the data from different organizations. In traditional machine learning, we take the grasses from different farms to feed the sheep. However, in the federated learning, we will move the sheep to different farms to eat the grasses, to eat the grass. Once the sheep become available or the model become available, the data, the organizer who providing the data can benefit from it. So typically, data have different distributed. The data has different distributions types. Depend on the differences of the features and the samples. Federated learning has two catalogs. They are horizontal federated learning and the vertical federated learning. Horizontal federated learning is also called sample partitioned federated learning or homogeneous federated learning, which means datasets share the same feature space, but differ in samples. With horizontal federated learning, we can make use of the relatively small partial dataset. It's a big one to increase the performance of a trained model. Vertically federated learning is also called feature partitioned federated learning or heterogeneous federated learning, which applies to the case that two or more datasets with different feature space share the same sample ID. With vertical federated learning, we can train a model with attributes from different organizations of the full profile. Here are some details of the example. The first one is anti-money laundering through multiple banks. And this is a horizontal use case. Different banks can cooperate to train a model with their data. The global model will improve about 14% occurrences against the model only trained by the local data. And the second is the risk management for predicting small and micro enterprises, which is a vertical federated learning use case. In the past, when a bank tried to loan money to the industry, it is dependent on the central bank's credit report. However, with federated learning, the brain can extend the view of this enterprise so that it can get more details about the risks of the enterprise. Okay, we just ran through the background of the federated learning. Next, we will focus on the implementation. Currently, there are several available projects in this area. For example, the Fate, the PY sheet from the OpenMind, and the TensorFlow from the TensorFL and the TensorFL from Google. However, the Fate project is the most industry-ready project among them. As the slide shows, the Fate is an actively open source project that holds by the Linux Foundation. It supports both horizontal and vertical federated learning. Fate itself is a distributed system which is composed of multiple series. So on the right-hand side is the overall architecture of the Fate. You can check more details in this GitHub repo. And I want to emphasize that the Fate project is the only open source and supporting the feature partition, which is the heterogeneous federated learning solution by now. And here are some details of and here there's some detail of the algorithms in Fate. At the lowest level is the MPC module, which stands for multiple party computing. On the top of it are some out-of-box machine learning algorithms in both horizontal and vertical ways. Fate also have some useful vertical feature engineering methods. For more details about them, please go visit the GitHub repo. Yeah, as we mentioned before, the Fate is a distributed system, which is composed of many series. It brings some challenges to the class management. To address this, we have another project called Cubafe, which manages the Fate class with cloud-native technology. Currently, the Cubafe project supports two types of backend to provision Fate. The Docker Compose targets the dev environment, and the Kubernetes targets the production environment. For more details, please check out this GitHub repo. So right now, we have gone through the entire background of the federated learning. Next, we'll talk about why Pulsar is necessary in the federated learning area, and how to integrate the Pulsar in the Fate. Firstly, let's take a look at this comparison. Typically, the communication is in distributed learning happened inside a data center, and messages will be transferred through the local network. And during the training, a server will only transfer data after several after multiple iterations. However, in the federated learning, several transmissions will happen within an iteration. And usually, this message will be transferred through the WAN, since the participants may be the different organizations and companies. And most importantly, the messages to send are encrypted, which will be around 13 times of the original size, which is around 30 times of the original data size. So due to the properties of the communication, we think that the message queue might be a solution to address these challenges. So the message queue project, some message queue projects like Pulsar, Kafka, and RabbitMQ has the mirroring mechanism, which has advantages like stable, support data intensive scenario, and designed for the transferring data on the RAN. This slide shows the overall architecture of the fake class with message queue included. So in this architecture, the most important service is so-called the fake flow service. It is the entry point of the whole class. It is also responsible for pipeline jobs. Below is a Spark. Below is a Spark class providing computing resource, and the HDFX class providing the storage resource. The fake board is the virtualization service. An NGX service is introduced to synchronize the pipeline between different participants of the federated learning. And the message queue is used to transfer the encrypted data during the training. So in the first version of the implementation, we use the RabbitMQ, but the performance is not expected, especially in the big data scenario. So we start investigating the Pulsar. Here are some key features of Pulsar. I may not list all of them, all key features of the Pulsar. But for us, the most important feature is the geo replication. The second one is the message compressions, which can reduce the size of message. You also require low latency. And Pulsar's cloud-native architecture make it easy to be managed on the top of a Kubernetes. As the diagram on the right-hand side shows, a Pulsar cluster is composed of three components. The first part is the broker to process and load balance the message. The second one is the bookkeeper class to persist the message. And the zookeeper class is to store the metadata for coordinations. The computing and storage separated architecture, making it easy to extend. This feature is significant with business growth. In case someone is not familiar with the geo replication, Here are some explanation. So with the geo-replication, message inside one topic can be replicated to another Pulsar class. For example, with the geo-replication feature, the topic A-B in the class A could be replicated to the class B. The message produced by the producer P1 can be controlled by both consumer C1 and C2. If a user enables the subscription replicating flag, the consuming state of the message will be replicated to the other class as well. However, to replicate messages among 3 Pulsar classes will be a little bit complicated. As for the topic A-B-C, Pulsar class A need to connect to other 2 Pulsar clusters directly. Once the producer P2 sends a message to the topic A-B-C, the message will be replicated simultaneously to 2 other clusters. But if we remove the line between Pulsar class A and B, class B will not receive any message. This is because the Pulsar class only allow replicate message join once. This is the fail-on spark with Pulsar. During the training, the original data will be split into several partitions, and each spark executor holds one of the partitions. Within an iteration of training, the Fate will create a corresponding topic on the Pulsar to transfer the partition of the data. Once the iteration is finished, relevant topic will be removed. And then in the next iteration, it will start over the same procedures. So the topic's correction is really important in our scenario. Typically, the time of the topic creation is much more shorter than the data transmission time. With the help of the Pulsar, the Fate can compose the star network, which allows a party to discover other party with a central service. This service is called exchange. As you can see, the exchange is composed of 2 services. The first one is NGX service. As we mentioned before, the NGX is used to synchronize the pipeline between different participants of the Federated Learning. And the ATX Apache traffic server is an SN9 Proxy to route data among different browser classes. As this diagram shows, compared to the peer-to-peer connect of the Pulsar class, this star network model will significantly reduce the maintenance cost. And this is the details of the SN9 Proxy. Overall, it is based on the TLX protocol. So in the first step, the client sends TLS hello message with the SN9 value, specifying the remote host we wanted to access. So the next step, when the SN9 proxy server receives the message, we will extract the SN9 value and check its root table, create a TCP tunnel to the remote host, and finally forwards the hello message to the host. Once the proxies receive the response from the server, it will forward it to the client, and then the client will have the further processing until the TLS connection is successfully created. Okay, we have gone through all content of this section. Here are some summaries. So overall, the federated learning is data-intensive workload. We introduce a message queue to transfer the data in the federated learning. We use Pulsar because it is cloud-native architecture and supports the star networking. Also, it provides more stable and throughput comparing other MQ projects. And finally, Pulsar also provides multiple subscription modes and message compression to improve the messaging performance. So currently, the Pulsar integration in Fate is in the very early stage. In the future, we will have further integration. We believe that tuning is necessary to gain better performance. It's necessary to gain better performance. Currently, and second, currently, Fate only leverage the messaging features of the Pulsar. So in the future, we will introduce more powerful feature like function monitoring to the Fate. We hope we can use Pulsar for ETL. We also hope we can use Pulsar for ETL job scheduling in Fate. And finally, in the Cubafe, we'll support deploy the Pulsar class on the Kubernetes. That's all of my section. Thank you for your attention. Bye.